So in this video, I am going to continue the discussion about using the Fourier series. So the Fourier series, as I said in the previous one, is nice because you can take any function and break it down into a sum of sines and cosine functions. Now the interesting thing is if we go over here and take a look at this part of this simulation. So this is a simulation by the PHY350 group at University of Colorado at Boulder. And now what they've done is they've added in the middle one a whole lot, hundreds of different wave contributions to it. And you can actually see what the wave contributions are. In the top wave, they're showing the amplitudes, and you can see the amplitudes of all the different wave numbers that are added in here. So there are hundreds of waves, so hundreds of wave numbers. And when you add all those up, what you get on the bottom is what looks like essentially just this particle added together. And so you can play around with this and you can change the number of amplitudes that you have. So I can add a lot of them in, which would then kind of fill in now this kind of wave particle that I'm building. I could change the I can change the relative position of those amp. I can select different wave numbers as opposed to others. But in the end, it's just a decomposition of all of those waves added together to make another function. The interesting thing, and this may be hard to see, is that if I look down here in this square over in this set of scroll bars over here, what I see is I see the uncertainty, the width of the wave number k, as well as the wave number in x. And so right now the x is very well defined. So my position of my new wave particle is very well defined, but to do that I have to fill in a whole bunch of waves. So I'm not really sure what wave is making the contribution. It's a sum of all the waves. If I now select a very specific wave, just one single wave, I have one wave right here, and you notice now that I get basically this single wave, and when I have only one wave, the contribution is one wave. So my particle now is spread out over a large distance x. It's now spread out over the distance. So if I restrict it to one wave, then I don't really know where the particle is. The particle's everywhere. It's spread out over the wave. Whereas if I constrain myself to knowing the specific position of the particle, I've now spread out the information of the waves. So the book has a good picture of that. And so here's a picture in the book where it shows the contribution of all of these different waves, and they kind of line up right here in the middle to give you a nice, good constructive interference, which gives you a very large amplitude. But over here, these waves are now adding together destructively, which lowers the amplitude. And that's what kind of gives me this packet shape. The fact that I have a lot of waves in constructive interference and a lot of waves on the fringes having destructive interference. Okay, now what does that mean in terms of what we're talking about with this Fourier series? Well, the neat thing about the Fourier is that it also is something called a Fourier transform, where I can write my function now, f, as a function of the information in the wavelength space, so a function of the wave number, times this transformation of a cosine kx, and then integrate over all space, all space dk. So it's interesting that if we sum up over all of the different waves and then multiply by the transform function cosine, we can get the function in terms of the x position, in terms of its position information. So this ak is called the Fourier transform. And the f of x tells us the spatial position or the spatial description of whatever it is that I'm trying to measure. And so if I go back to the simulation, the top graph is the a as a function of k. This gives us the wave information. So I'm calling the wave space this abstract space, which is a function of the wave number. The one down here in the bottom is the position space, spatial space, the position space information, how the wave spreads out over a distance x. And the really interesting thing is that those two things from Fourier series play off each other. So the width of one times the width of another is approximately 1. So that if I know the width of my my wave in space really, really well, so I narrow down where the position is, I lose the information in k, or I need a lot of different waves to isolate that position. And that's kind of what I did before when I was toggling back and forth on the graph to show that if you want to isolate the location of the thing, then you have to add in a lot of waves to do that destructive interference to isolate it. But if I just pick on one wave, that wave now loses the spatial information. Or it's a wave, it's periodic over the space. And so what you end up with is this. You also, and so what we have is something that looks like this. And so if I have just a few waves, right, then my knowledge of the wave space, the wave number, is very good. It's a very, it's a very well-defined quantity which wave it is. It's this wave, but that wave now spreads out over all space. If instead I constrain my object to a very small space in x, that now increases the number of waves you have to add in, so your information in wave space expands. Now, a more rigorous analysis of the Fourier is to look at the root mean square values. And when you do that, if you look at the RMS instead of just this width, then what you have is that the width is actually greater than or equal to 1/2. Okay, again, I'm not going to get into where that comes from, except for the fact to say that comes out of Fourier analysis. But again, the physics is that if you want to know where something is in particular, then you have to include a lot of waves to cancel out all of this stuff on the side here. But if you only want to know about one wave in particular, you lose any information about where you are in space. The wave is now a global object that now fills up the entire space with the crests and troughs. The interesting thing is you can do the same analysis with frequency, and what you find is that your the amount of information you know about the time times the frequency is also greater than or equal to 1/2. So it turns out time and frequency are coupled variables. Space and wave number are coupled variables. So where does quantum mechanics come into this? Well, if you remember from de Broglie that the momentum is h bar times the wave number k. So what this says is that I have to add different values of waves are going to give me different values of momentum. So when I put that into the equation for delta k, I have delta x times delta p divided by h bar is greater than or equal to 1/2. If I multiply both sides by h bar, I get delta x delta p is greater than or equal to h bar over 2. And so I get this very interesting result called the Heisenberg uncertainty principle. Which you may have heard about before. But essentially, since momentum is related to the wave numbers, then the uncertainty in the momentum is now linked to the uncertainty in position. Or another way of saying is that if I really want to narrow down where something is, I want to find a very specific position, delta x. So delta x is really small. That means that the momentum uncertainty becomes very large. There has a large range of momentums now available to that particle because I've now tried to constrain it to a knowledge of its position really, really well. Or if I really try to constrain its knowledge of its momentum, if I make the error in the momentum small, the uncertainty about our knowledge of momentum is now small. I've chosen basically a very, very small range of momenta. Then its position knowledge becomes very large. The uncertainty in its position now becomes much bigger. And so they play off each other because the right-hand side of this equation is a constant. So one goes down, the other one has to go up. And so what we're left with is this kind of push and pull, that we can try and do a measurement where we know the position really, really well, but now what we've done is we've lost information about the momentum. Or another way of saying is that there's a large range of momenta available to describe this problem. The interesting thing is the same is true now for time. Since the energy, according to Planck, is h bar times omega, then the uncertainty in the energy is related to our uncertainty in our frequency. And so we plug that in, we get delta t times delta E over h bar greater than or equal to 1/2. So delta t times delta E is greater than or equal to h bar over 2. So now our uncertainty in the energy, how well we've measured the energy in an experiment, is related to how well we can measure it in a certain period of time. And to me, that's really interesting because that's how things decay. And so if I look at a radioactive nucleus like uranium-238, uranium-238 has an uncertainty of basically 1 billion years. So 10 to the 9 years. That's a large uncertainty. Somewhere between now and 1 billion years from now is when that uranium nucleus is going to decay. But if the uncertainty in my knowledge of when it's going to decay is so large, that means the energy in that the knowledge of the energy level is really, really, really good. And so what you have is something, if you look at the energy levels of uranium-238, then what you have is these very narrow bands of where something is well known. So maybe one of them is not known as well, and so it has a larger delta E. This one is known really well, and so it's got a much smaller delta E. But that means that this energy level has a very long decay time, whereas this one has a much shorter decay time. It's probably going to decay maybe in 1,000 years, or the range of decays is maybe only in hundreds of years. But that hundreds of years means I don't know the energy of that level as precisely.